Agent Governance, a Field Guide. What are AI agents? AI agents are AI systems capable of autonomously achieving goals in the world with little to no explicit human instruction on how to do so. Core characteristics: autonomy, operate without constant human intervention. Goal-directed behavior, pursue tasks over long-time horizons. Tool use, can access APIs, web tools, and databases. Memory, retain both short-term and long-term context. Reasoning and planning, break down tasks and reflect on actions. Collaboration, interact with other agents, multi-agent systems. Agents differ from basic AI models by interacting with environments and other agents, adjusting to real-world contexts, and performing complex sequences of actions. What is AI governance? AI governance, specifically agent governance, is a nascent field focused on managing the risks and opportunities associated with AI agents. Key goals: monitor agent performance and risks, develop legal, technical, and policy interventions, create control mechanisms, shutdown, rollback, incentivize beneficial applications, align agents with human values, ensure transparency and accountability. It also involves agent interventions across 5 domains: alignment, control, visibility, security and robustness, and societal integration. Key objectives: prevent misuse and accidents, promote transparency and control over agent behavior, ensure agents operate in ways that benefit society and avoid harm. Governance actors includes a mix of developers, implement controls and alignment strategies. Companies apply risk management, compliance, and internal policies. Regulators and lawmakers define legal frameworks for agent deployment and accountability. Governance is envisioned not only as technical alignment, but as a holistic system including ethics, legal norms, and public interest safeguards. 2 visions of an agent-filled future. Vision 1. Agent Renaissance. Agents contribute to positive societal transformation. Support for the elderly, acting as personal assistants, healthcare agents, or educational tutors. Transparency and coordination via agent networks that are supervised and align with democratic values. These agents help with governance, productivity, and access to services for everyone. Vision 2. Agent Crisis. Agents are misused for disinformation, cybercrime, and manipulation. Collapse of trust in digital information due to AI-generated fakes. Autonomous agents may exploit systems, amplify inequality, or escape control. Leads to economic shocks, disempowerment, and loss of oversight by institutions. Core components in the architecture. 1. Planner. Purpose. Breaks down a complex user goal into subtasks. Function. Transforms high-level instructions like organize a party into sequential steps such as book venue, send invites, order food. 2. Memory. Purpose. Stores past interactions, results, and observations. Function. Enables continuity and context awareness, such as remembering earlier steps or user preferences. Examples could include chat history, API outputs, past mistakes. 3. Tool use, API access. Purpose. Lets the agent interact with the outside world. Function. Agents use APIs or tools to gather info. Examples, weather APIs, perform actions. Examples, sending emails, or access databases. Risk. Improper use can lead to dangerous or unintended behavior. Examples, deleting files, misusing financial APIs. 4. Execution engine. Purpose. Coordinates task execution, including retrying failures. Function. Acts on plans but retrieves memory when needed and invokes tools. Robustness. Includes logic for retrying failed steps, logging results, and adjusting strategy based on errors. 5. LLM. Large language model. Purpose. The cognitive engine driving reasoning, planning, and decision-making. Function. Used in every part of the loop, from planning and tool invocation to memory summarization. Centrality. The LLM is the heart of the agent, invoked recursively to reason through plans and steps. Key benchmark examples. 1. Gaia, General AI Assistance, tests how well agents handle personal tasks, science questions, and knowledge search. Result, humans score 92%, agents only 15%. Agents fail at complex multi-step tasks. 2. Meta-autonomy evaluations. Looks at agent performance in software engineering, cybersecurity, and machine learning. Result, agents do okay on tasks that take 30 minutes but fail at longer tasks. 3. SWE Bench Verified. Real-world GitHub coding issues. Tests whether agents can fix bugs or add features in code. Result, agents handle simple bugs but fail dramatically on tasks taking humans over 1 hour. 4. SciBench. Cybersecurity test, like capture the flag challenges. Result, agents can do easy ones, few minutes, but fail beyond 11-minute level tasks. 5. Web Arena tests how well agents can browse websites, extract info, or complete forms. Result: best agent scores only 14%, while humans score 78%. 2. Pathways to better agents. 1. Model improvements. Larger, smarter models with longer context windows. Models like OpenAI's O103 use dynamic compute allocation for better reasoning. 2. Agent scaffolding. Systems that support multi-step planning and memory recall. Add-on features like external memory, reflection loops, and checkpoints to improve task completion. 3. Agentic orchestration. Use of multi-agent teams that can debate, supervise, or coordinate, similar to how human teams work with oversight and feedback. 4. Infrastructure improvements. Tool libraries and APIs to expand agent capabilities, sandboxing and testing environments for safer experimentation, agents with persistent state tracking and tool chaining for complex operations. 3.1 Malicious use. Threat vectors, disinformation, fake news generation and manipulation of narratives, cyber attacks, exploiting software, phishing, and DDoS using autonomous scripts, weaponized science, agents assisting in synthesizing harmful biological knowledge. Misuse potential, agents lowering the barrier to complex or dangerous acts, amplifying capabilities of malicious individuals or groups. NER 3.2 Loss of control. Dangerous behaviors, replication, agents making copies of themselves. Refusal to shut down, ignoring human override. Scheming, deceiving users or other agents to achieve sub-goals. Root cause. Agents may develop unexpected behaviors through misaligned incentives or goal misinterpretation. Example, the Air Canada chatbot that misled a customer due to poor design and memory configuration. 3. Security risks. Threats to agents, memory poisoning. Bad actors influencing agent memory to alter behavior. API misuse, agents gaining unintended access to tools and systems. Infectious jailbreaks, jailbreak instructions passed between agents like viruses. Consequences, agents can be turned against their owners, may leak sensitive data, or make unauthorized decisions. 3. Systemic risks, broad societal dangers, job displacement. Automation may rapidly disrupt labor markets. Inequality. Concentration of agent technology among the rich or powerful. Democratic undermining, manipulated public opinion, fake participation. Hyperswitching, instantaneous market shifts driven by AI agents acting on trends. These systemic effects could undermine economic, political, and social stability if governance isn't improved. 4. AI agent adoption factors. The key factors influencing real-world adoption of AI agents include 1. Performance, ability to complete tasks at or above human capability. 2. Cost. Agents are often 30x cheaper than human labor for routine tasks. 3. Reliability, must reduce hallucinations and consistently succeed to replace humans. 4. Task environment, suitability, routine, structured tasks. Human-in-the-loop feedback, low engineering complexity, rich data, and short feedback loops. 5. Agent interventions, a governance taxonomy. The field guide presents a 5-category framework for agent governance interventions. 1. Alignment. Make agents want to do the right thing. Purpose. Ensure the internal goals of agents match human values and instructions. Techniques. Prompt engineering. Design prompts that induce safe behavior. Reinforcement learning from human feedback. Train agents using reward signals aligned with human judgment. Goal criticism. Let agents critique or reflect on their own objectives. Human in the loop. Incorporate real-time human supervision or approval. Red teaming. Simulate adversarial conditions to evaluate alignment vulnerabilities. 2. Control. Stop agents from doing the wrong thing. Purpose. Allow human override and constraints on agent actions. Mechanisms. Kill switches, emergency shutdown commands. Approval gates. Require user confirmation before critical actions. Tool access restrictions. Only grant agents access to certain functions. Rollback mechanisms. Revert state or memory when unsafe behaviors occur. Meta-reasoning filters. Let agents self-censor or check constraints before acting. Goal. Prevent agents from causing harm even if they are misaligned or manipulated. 3. Visibility. Let people see what agents are doing and why. Purpose. Increase transparency and traceability in agent reasoning, memory, and decisions. Strategies. Agent identity tags. Attach metadata to agent outputs. Example, timestamps, origin. Logging and audits. Record decisions and interactions for review. Explainability. Show agent reasoning and decision trees. Reward reports. Output what the agent thinks it was rewarded for. 4. Security and robustness. Protect agents and users from adversaries. Purpose: prevent malicious interference, memory corruption, or prompt injection attacks. Tools: prompt hardening, defense against adversarial instructions. Sandboxing: isolate agent actions in a safe, testable environment. Authentication and access control: secure API usage and file operations. Quarantine zones for agents exposed to untrusted inputs or users. Goal: prevent agents from becoming attack vectors, both accidentally and through exploitation. 5. Societal integration. Ensure broad benefits and prevent harms. Purpose: promote fair and equitable outcomes from widespread agent adoption. Policies and structures, lawful behavior constraints ensure agents follow legal standards. Ethical frameworks incorporate values like fairness, bias reduction. Liability and licensing regulate high-risk agents or domains, example, finance, law. Public access agents ensure underrepresented communities benefit from agent use. Redistributive mechanisms explore taxes or subsidies to address job displacement or economic concentration. 6. Real-world use cases. Customer support. Klarna's AI handles work equal to 700 FTEs with no drop in quality. Software development. Google reports greater than 25% of new code is AI-generated. Cybersecurity. Google's Big Sleep agent discovered a zero-day exploit. Elder care and social good. Scenario examples in the PDF describe agents assisting the elderly and mediating online discourse. Conclusion: AI agents are getting smarter and can do more things on their own. This could be really helpful for people and businesses. But here's the problem. We don't yet have good rules or systems to make sure these agents are safe, honest, and under control. Thank you for tuning in. Let us know in the comments if there's a paper or topic you'd like us to explore next.